the second part of this lesson, we are going to dive a little bit deeper. You will need your trig identity sheet because we're going to expand upon the sum and difference identity into the bottom two boxes within our identity sheet, the product to sum identities and then sum to product identities, and how we can use them in a solving type manner. From our last lesson, we learned how to take 3 times sine of 2x plus 4 times cosine of 2x equals to 1. We focused on the left-hand side, turning that into a single sinusoidal function. So let's do that from our last lesson with this particular one, and then we can solve from there, because we're needing to find at least two positive solutions here. So in this case, I know that my m value is 3, b is 2x, n is 4, and again, b is 2x. All right, so a squared is 3 squared plus 4 squared. That gives us 25, so a has to be 5. Then we will find cosine of c, so that we can find our c value, is our m value over our a value. And unfortunately, that's not a unit circle friendly value, so I need to use my inverse. So by definition, the inverse of cosine of 3/5 is approximately 0.927 in radians when I plop that into my calculator. Looking at sine of c, this is equal to our n value over our a value. Again, not in our unit circle. So by definition, the inverse of sine of 4/5 is also approximately 0.927 is what we need. So now that we didn't have to find another solution. We certainly could have, because I know cosine. If I am here, I could also find cosine down in the fourth quadrant as well. So if these wouldn't have matched, I could have said, or we could have taken 2 pi minus 0.927 and said that one of my answers could have been about 5.356. And then done the same with sine, right? So what we know about finding those solutions around the unit circle. But now that I have my a, b, and c, coincidentally, just by using the first option, I'm going to rewrite this 3 times sine of 2x plus 4 times cosine of 2x as a single sinusoidal function that will be useful for us. So that's a, which is 5 times sine of b, 2x, plus 0.927 is equal to 1. I could get sine by itself by dividing both sides by 5. Okay. And now we've got some stuff on the inside, so we are going to need to utilize u substitution to help us. Right now I have sine of u is 1/5. Well, 1/5 is not on our unit circle. Thus, by definition, the inverse of sine of 1/5 is equal to u. I'll bring this all the way up here. By putting that into our calculator then, u has to be 0.201. But I also know, so right now here's sine of 1/5, but I also know sine is positive in the second quadrant. So if here to here is 0.201, I also need to know what is from here to here as an option as its reflection, which I can find by taking pi minus 0.201 to obtain 2.940. We also may need to have more than one solution when we start solving. So although I have 0.201 and I have 2.940, it may be best to also find another solution around the unit circle, so that if I were to take this particular one and go all the way around and come back to it, what are three different ones that I can find? And I'm just foreshadowing a little bit here to reach that conclusion. Not all the time we'll need it, but we also could have 0.201 and adding 2 pi to that, going all the way around the unit circle to give us approximately 6.485. All right, so these values are all equal to u. We need to find two positive solutions. So now that I have what u is, we can substitute back so that we can actually find what x is. Right, so we'll have 2x plus 0.927 equals our first u. Two x plus 0.927 equals our second u from the second quadrant. And then I'll also have 2x plus 0.927 equals my third u, just giving us a little assurance because we need positive solutions. Notice what's going to happen here as I start to solve for x. When I subtract 0.927, this is going to give us a negative solution, right? We're looking for positive solutions. So this one doesn't matter anymore. That's why I needed to find a second round to get that 6.485 location. Then solving for x in both locations, I will end up with 1.007 and x will equal 2.779. There was a lot of room for error, a lot of room for rounding in many locations, so it's okay that my solutions in my graph are just slightly off in that thousands place. But I'm going to use graphing to help verify, just because, again, there's a lot of room for error unintentionally throughout this entire process. So I did use the intersect method. So I've got the left side of the graph, and I have the right side of my graph here. And notice because the right side was a constant, if I just put 1 into Desmos, it's not going to know how to graph that, which is why we have it set to y equals 1. You could also set this equal to y equals as well, if that's helpful. And then where is our first positive 2 locations in which they intersect? So the blue line, of course, is my horizontal line, and I see that they intersect at 1.006 and at 2.779, which is where we had found algebraically that they would match with one another. So on our next example, we're going to utilize our product to sum identities, and these product to sum identities are on our identity sheet on the bottom left-hand side. So I've got 4 different ones on the bottom left-hand side, but I've only got 3 of them written here, but there are 4 of them that you can find. It's asking us to rewrite sine of 2x times sine of 4x as a sum or difference. So I'm having sine times sine. So when I look at my product to sum identities here, I'm going to be utilizing this particular identity because that's sine times sine, where alpha is 2x and beta is 4x. I can then rewrite this using that identity as 1/2 times cosine of alpha minus beta, so 2x minus 4x, minus cosine of adding them, so 2x plus 4x. I'll go ahead and simplify inside, giving us cosine of negative 2x minus cosine of 6x. I'm going to utilize our even-odd identity because I have cosine of a negative value, so even-odd identity. Is cosine of positive 2x minus cosine of 6x. And then I'm going to distribute my 1/2 for a final solution of 1/2 times cosine of 2x minus 1/2 times cosine of 6x. On the right-hand side, for example 11, we can also use this with radians, so perhaps we'll be able to simplify once we add or subtract here, but I've got cosine times cosine. So we're going to utilize this bottom product to sum, cosine times cosine, where I've got alpha as 11 pi over 12 and beta as pi over 12. All right, so this can be rewritten as 1/2 times cosine of adding 11 pi over 12 plus pi over 12 plus cosine of their difference, 11 pi over 12 minus pi over 12. I'll complete the sum and difference inside. Cosine, that gives me 12 over 12, which we know is the same as just pi. And then I'll have 10 pi over 12, which I also know is 5 pi over 6 when we reduce. I know that cosine of pi is -1. And I know that cosine of pi over 6 is -√3 over 2. So let's go ahead and distribute to eliminate our parentheses or our brackets, or -1/2 minus √3 over 4. I could combine these into one because I know -1/2 is the same as -2/4. So this could be the same as -2 minus √3 all over 4, which is typical how we would write two fractions that we could combine together. Moving to the right-hand side then, the bottom right-hand side, if we can go product to sum, we can write something as sum to product. And in this case, we could also do sum or difference to product, right? I have cosine of 15 degrees minus cosine of 75 degrees. So I've got cosine minus cosine. So we'll write it as such, where in this case, 15 degrees is U and 75 degrees is V. All right, so we'll have -2 times sine of adding them together, divide by 2, 15 plus 75 divide by 2, times sine of their difference, 15 minus 75 divide by 2. Thus we'll have -2 times sine of 45, since 15 and 75 is 90. 90 divided by 2 is 45 degrees. And 15 minus 75 is -60 divided by 2, so -30 degrees. Remember, -30 degrees, we're going clockwise on our unit circle. Sine of 45 degrees is √2 over 2. Going clockwise, -30 degrees, or of course, if you would prefer, we could take -30 plus 360 and evaluate at sine of 330, if that's better for you. But it is -1/2 on the unit circle. reducing all of this, let's see, here and here, we'll have let's see what we can reduce here and here. So it looks like we'll have positive square root 2 over 2 after we evaluate. Let's prove the identity. I did bring over the sum to product identities as it most likely will be useful, as we notice the left-hand side of what we need to prove. Both here and here appear as if we can utilize the sum to product identities to see what we can come up with. So I've got cosine minus cosine. So my numerator we could rewrite here. And our denominator is sine plus sine. So we can use that here and see what we come up with. So 4x and 2x, we've got u and v respectively for each one. Okay. Let's see what we got. We'll have negative 2. We'll start with the numerator first, times sine of 4x plus 2x over 2 times sine of their difference, 4x minus 2x over 2. So we certainly are making this look more complicated before we make it easier for ourselves. Notice here though, I have a positive 2, not negative. So positive 2 times sine of u plus v, 4x plus 2x over 2 times cosine of their difference. All right, negative 2 times sine of 3x, since we'll have 6x divided by 2, times sine of just x. 2 times sine of 3x, again we'll have 6x divided by 2 times cosine of x. Notice we are in multiplication, and so we are able to eliminate common factors. I have a common factor of sine of 3x, which we can eliminate, and I have 2 and 2. So all that's left is negative sine of x over cosine. And we know that sine over cosine is tangent, but with this negative gives us negative tangent of x. And we have proven then that the left side is equivalent to the right side. Last example here is showcasing utilizing just graphing how we can find the solutions. So we've got sine of pi times t plus sine of 3 pi t equals cosine of pi t for all solutions that are between 0 and 2. So in this particular method, I utilized the intersect method. So I have the left side of my graph here and the right side of my graph here. Instead of using t, I used x so that Desmos could graph it nicely for us. So I want to know where are my green line and my purple line intersecting one another. And we want all of them between 0 and 2. So here I find 2. Notice it's not equal to 2. So where are my solutions between 0 and 2? And where are they intersecting? So we've got a few solutions. It appears as if I have 0.083 as one solution. We have another solution where they intersect at 0.417. They intersect at half. They intersect down below at 1.083 and at 1.417, and finally at 1 1/2. So it looks like we have 1, 2, 3, 4, 5, 6 solutions in between 0 and 2. And then it looks like we would repeat ourselves starting with this. So that's probably why we go from 0 to 2, because then we would start to repeat ourselves. Okay, so these 6 solutions are what we'd be looking for. The alternative is to find the 0 method. So all I had done from the previous equation here, the original that we were given, is subtract cosine of pi t and bring it to the left-hand side such that our equation is equal to 0, so that this would be equal to 0. And of course, this is the 0 method, so we would want to find where our graph crosses the x-axis between 0 and 2. So here is 2 here is 0, and I notice the same 6 solutions are crossing the x-axis that we had found with the intersect. So finding where it crosses the x-axis is similar to the intersect. We're still going to have the same solutions. It just depends your preferred viewing of the graph itself. But that takes care of all of lesson 7.2.